Welcome to a lesson on exponential functions. An exponential function is a function in the form f of x equals a times b raised to the power of x, where a can't equal 0, b must be greater than 0, and b can't equal 1. If a was equal to 0, or b was equal to 1, we would have a constant function, not an exponential function. The value of a is called the initial value or starting value, which is the function value when the input x is equal to 0. And therefore a also gives us the vertical intercept, which would be the ordered pair 0, a. The base b is called the growth factor or decay factor, where the base b equals 1 plus r, where r is equal to the growth rate per unit of time as a decimal. So if the base b is greater than 1, then r, the growth rate, would have to be greater than 0 or positive, and therefore the function represents exponential growth, which is a function increasing at a constant percentage with the growth rate of r. Now, if the base b is between 0 and 1, that means r, the growth rate, would be negative or less than 0, and therefore the function represents exponential decay, which is a function decreasing at a constant percentage, and the decay rate is equal to the absolute value of r. Now let's take a look at exponential growth and decay graphically. Here we have the graph of f of x equals 3 times 2 raised to the power of x. Notice how the base b is greater than 1, and therefore we have exponential growth, meaning as x increases, the function values also increase. Now, because we know the base b is equal to 1 plus r, it's also true that r, the growth rate, is equal to b minus 1. So in this case, notice that b is equal to 2, and therefore r would be equal to 2 minus 1, or 1. So if r is equal to 1, that means we have a growth rate of 100%, which means we have the doubling function because notice how the base is 2. Looking at the table of values, we can also see that as x increases, f of x also increases, and it actually doubles as x increases by 1. Now looking at the function here on the right, notice how the base b is between 0 and 1, and therefore we have exponential decay, and therefore we have a function that decreases at a constant percentage, so as x increases, the function values decrease. And in this case, because the base b is equal to 1/2, we can say that r equals b minus 1, or in this case, r equals 1/2 minus 1, which equals negative 1/2. Notice here the growth rate is negative 0.5 or negative 50%, which again means we have exponential decay. We have a decay rate of 50%. And because the base is 1/2, we can say this is the halving function. Notice as x increases, f of x decreases. In fact, as x increases by 1, the function values decrease by 50%, or by half. One more thing to notice about both of these functions is notice that a, the initial value, is equal to 3, which also gives us the vertical intercept for both functions. Now let's look at some applications of exponential functions. Here we're told the population of Flagstaff, Arizona was approximately 65,000 in 2010 and was growing at a rate of 3.9% per year. We're asked to write the exponential function to model the population. Let t be the number of years since 2010, and p of t be the population in thousands. Then we'll predict the population in the year 2017, and then predict when the population will reach 100,000. So for part A, our function p of t is going to be in the form of a times b raised to the power of t, again because we have a function of t, where a is equal to the initial or starting amount, the base b equals 1 plus r, where r is equal to the growth rate. So the first thing we might notice here is that r is going to be 3.9%, which is a decimal, would be 0.039. Now let's find the value of a, the initial amount. Because t is a number of years since 2010, the population of 2010 will help us determine the initial amount, a. Notice how the population in 2010 is 65,000, but because the function value p of t is the population in thousands, a is not 65,000, a is 65. This is all we need in order to write our exponential function. We would have p of t equals 65 times, again the base is 1 plus r, so we have 1 plus 0.039 raised to the power of t. So simplifying, our population function p of t is equal to 65 times 1.039 raised to the power of t. And now we can use this function to answer parts B and C. Part B, we're asked to predict the population in the year 2017. Remember, t is a number of years after 2010, so t is going to be equal to 7. But if we have a hard time determining t, we can always determine t by starting with the desired year and subtracting the base year, which will give us the correct value of t, which in this case is 7. So we want to find the function value p of 7 to predict the population in the year 2017. So we'd have 65 times 1.039 to the power of 7. And now we'll go to the calculator to approximate this function value. But remember, p of 7 is going to be in thousands. So we have 65, and then in parentheses we have 1.039. This is raised to the power of 7. Enter. So because this function value is in thousands, let's round this to 3 decimal places, which would be approximately 84.962. Again, this is in thousands. So if we want to convert this to the number of people, we would multiply by 1,000, which would give us 84,962 people. So as a complete sentence, we can say in 2017, the population is predicted to be 84,962. Now for part C, we're asked to predict when the population will reach 100,000. So we're trying to find the year in which the population is going to reach 100,000. So we're given a function value, and we want to find the value of t. But because the p of t is in thousands, we need to recognize here that we're trying to solve this equation when p of t equals 100, because p of t equal to 100 does represent a population of 100,000. So we want to solve the equation 100 equals 65 times 1.039 raised to the power of t. And we'll solve this 2 ways. We'll first solve this graphically, just in case you haven't learned about logarithms yet, and then we'll solve it a second way using logarithms. To solve this graphically, we would use the graphing calculator and enter the right side in y1, then the left side in y2, then determine the point of intersection of y1 and y2 to determine the value of t that satisfies this equation. So with the calculator, I've already done some of this to save some time. If we press y equals, notice how I've entered the right side in y1, though I used x instead of t for the variable, and I entered the left side in y2. Now before we graph this, we want to make sure we can determine the point of intersection, so we do have to adjust the window, which again I've already done to save time. We press the window key. Notice how I changed the x-axis, or the horizontal axis, from -5 to 40 by 5s, and the y-axis from -20 to 140 by 20s. Now we'll go ahead and press graph. So there's the exponential function, and here's the constant function y equals 100. And our goal here is to find the x-coordinate, or in this case the t-coordinate, of this point of intersection. So we'll press second trace for the calculation menu, option 5 for intersection, and now we can just press enter 3 times. So enter, enter, enter. Notice how we get t, or in this case x, is approximately 11.26. So graphically we know the solution is t is approximately 11.26, but now let's also solve this using logarithms. So to solve this algebraically using logarithms, the first step is to isolate the exponential part by dividing both sides by 65. 100 divided by 65 simplifies to 20/13. So we have 20/13 equals 1.039 raised to the power of t. And here's where we'll have to use logarithms in order to solve for t. Because we'll be using the calculator, we'll use either a common log or natural log. In this example, let's use the common log. So we'll take the common log, or log base 10, on both sides of the equation. So now we have log of 20/13 equals, now on the right side we can apply the power property of logarithms shown here below, where we can take this exponent here of t and write this as a product. We would have t times the common log of 1.039, and therefore in order to solve for t here, we would divide both sides by common log of 1.039. Simplifying on the right, this simplifies nicely to t, and now we'll approximate this quotient on the calculator, which again we know should be 11.26. So going back to the home screen, we have common log of 20/13 divided by the common log of 1.039. Enter, and notice how we do get the same value for t, approximately 11.26. So this tells us that we predict the population will reach 100,000 approximately 11.26 years after 2010. Now determining what year this should actually be in can be a little bit tricky. If t was equal to 11, then that would be the year 2010 plus 11, which equals 2021. But this would be the end of the year 2021. So for any value greater than 11 and less than 12, it would actually be sometime in the following year of 2022. So to put this in a sentence, we'll say we predict the population to reach 100,000 in 2022. Again, this idea of what year it is can be a little bit tricky because sometimes some textbooks actually would take the value of t, which is approximately 11.26, and round to the nearest year of 11 and say the year is 2021. But any value more than 11 and less than 12 would actually be in the following year, which would be the year 2022. I think we'll stop here for part 1. In part 2, we'll take a look at an example of exponential decay. I hope you found this helpful.